Hi, my name is Annie Bakker, and I'm here to present our master's and PhD topic entitled A Digital Twin Pump Laboratory for Water Asset Management. And this project will be supervised by myself in partnership with Dr. Karel Creer and Professor Anton Basson. This project stems from work and funding provided by the Rand Water Board towards my new position at the university as the Mechanical Research Chair for Rand Water. This is a new direction of research for us, and in order to give some background, I'm going to briefly cover our proposal for the Rand Water Mechanical Engineering Research Chair, as well as the supporting facilities. Basically, Industry 4.0 is by now affecting every conceivable industry, with its focus on interconnectivity, automation, machine learning, and real-time data. The equivalent of Industry 4.0 in the water sector is termed Water 4.0 or digital water, where there's a merging of cyber and physical worlds to create a better understanding of water management systems. And specifically, we aim to apply this towards real-time data and algorithms to enable early warning and decision-making processes pertaining to water asset management. A very important concept in Industry 4.0 is that of a digital twin. So these are assets which are believed to be some of the main drivers of future business in every conceivable industry. Basically, a digital twin is defined as the representation of the state or behavior of a real asset through a digital counterpart within its operational context. And the aim of coupling a digital representation with a real asset would be to enable decision aiding for a user. And I'd like to borrow a bit from this demonstration video by the software company Ansys, who are really enabling digital twins through a platform they call Twin Builder.
For decades, companies have used simulation as a product development tool to discover failures and flaws in their designs. Now, engineers are using simulation after their products are built, sold, and deployed in the field. It's called a digital twin, a complete digital replica that operates in real time, giving engineers unprecedented visibility into the performance of their products. Here's a simple example. This industrial pump has multiple sensors providing real-time information. In this example, the sensor's data is fed into the IoT platform, where engineers can monitor the normal operations of the pump. Here, an anomaly is introduced, as a valve is closed, prompting an alert and the need to troubleshoot the problem. The Ansys simulation platform allows engineers to evaluate all possible inputs and operating conditions. Users can model a complete system and integrate live sensor data, creating a near real-time environment. By reproducing the problem virtually with the digital twin, you can identify and analyze the cause, purpose, and test corrective actions. When an anomaly is detected, Ansys takes data from the system model and sends it to the edge, on-prem data center, or cloud, allowing for automatic 3D simulation to model the specific nature of the problem. The digital twin allows for diagnosis and in-depth root cause analysis for physical assets in the field. Here, the root cause of the anomaly is identified by 3D simulation to be cavitation in the pump, as visualized by the purple vapor bubbles. The user can perform what-if scenarios on the digital twin for both testing and further optimization. With the Ansys platform, customized user experiences can be easily implemented. This allows for ease of use and communication through similar graphical interfaces that are customizable for each user. At this point, the user validates the corrective action found on the system model will remedy the problem on the physical asset through in-depth 3D on-demand simulation. Here, you can see that no more bubbles are present and the pump is once again operating properly. The cavitation issues have been corrected in the digital twin and can now be applied to its real-world counterpart. Digital twins require a complex and comprehensive knowledge of systems engineering. Only Ansys has the breadth and depth of simulation experience to bring the full power of digital twins to your engineering challenges.
Digital twins are very versatile in their application. and can be component-based, as per the previous example, or can be used to serve very large systems. Here is an example of the Shoaiba Phase 3 drinking water supply project in Saudi Arabia, where Fraunhofer Institute partnered with ABB to produce a leak detection system by modeling 1,600 kilometers of pipeline and supply from reservoirs. This system is represented by a digital model that calculates the measurement metrics at certain key points based on the temperature, flow rates, and reservoir levels. And by looking at real-time measurements at these same metric monitoring points and comparing this to the model, leaks can be detected and the performance of the system can be managed and faults can be localized. So against this backdrop, we thought about harnessing some of the advantage of our digital twins in our RAND water proposal. This includes bringing the power of simulation to operation. So this means that you are able to gain information about hazardous or remote operations by simulating this environment based on maybe some sensor inputs and the ability to deal with large volumes of information, which is too much for humans to process or too exhausting. This means that maybe we can automate some simple decisions and use the watchdog capabilities of computers, which never need to sleep. Computer models also give us predictive power. For instance, we can simulate what failures would look like on one-off builds and then monitor the response from a model and compare that with real-time measurements to give us an indication of early warning for failure. We can run what-if scenarios to check out hypotheses for important strategic decisions. And we can use new machine learning techniques to create models that learn from data. Also, computers give us the ability to recognize patterns from certain responses and to remember them forever. A key thing or a key concept about digital twins is that the mere gathering of data or the creation of complex models does not itself give decision aiding value. And this is where we would like to invite the systems design process into digital twins for water asset management. This means that a digital twin solution will be designed for the appropriate decision level, whether it be strategic, technical, or operational, and for the right temporal scale, whether it is to gather hindsight, insight, or foresight. Also, many systems today, when it comes to vibration monitoring and modeling, pertain to also many systems today have a monitoring capability. So that means that from real-time data, we are able to get some descriptive metrics about a system's response. And maybe with basic analytics, we can augment that to give diagnostic value. For instance, in gearbox monitoring or the monitoring of bearing failure. However, our focus is going to be to progress from diagnostic value towards predictive value or even prescriptive value, where we can say that a component will last this long and to prescribe a way in which a failure or a problem can be dealt with. Of course, the ultimate value of digital twins may lie in their potential autonomy, where large amounts of simple decisions are taken and the according actions are initiated without human interference. So for RAND Water, the proposal of our first master's project would be to create a digital twin of the pump test laboratory at Stellenbosch University. Here, 3 single-stage centrifugal pumps are coupled with PVC pipes. These pipes can be reconfigured to couple these pumps in series or in parallel. The pumps are driven by electric motors and equipped with variable speed drives. The idea would be to better equip the system with more measurements and to digitize them in order to be able to receive real-time information and to build more complex models on top of that, whether they be machine learning or physics-based models such as computational fluid dynamics, in order to simulate specified phenomena on these pumps. To gear these measurements and models towards the detection, diagnosis, and prognosis of anomalies and their effects, and perhaps to systematically induce fault in the system to see whether our models are indeed able to cope or to give the desired responses we anticipate. With our kickoff in 2020, the plan is to have a master's student in 2021-2022, ideally continuing towards a PhD, and as time progresses, to increasingly progress from the Stellenbosch pump test laboratory into the field and to trial some of these solutions on real infrastructure. The facilities at our disposal include the structural laboratory, the sound and vibration laboratory, which is expertly equipped with vibration sensors, data acquisition, and analysis software. The automation and design laboratory, which has a history in creating digital twins for the manufacturing industry. We hope that with the knowledge of Dr. Karel Creer and Prof. Anton Basson, we can also bring this expertise to water asset management. Finally, Stellenbosch University is also equipped with experts such as Prof. Johan van der Spey and very good licenses for finite elements and CFD. Looking a little bit broader, Stellenbosch University houses the Water Institute. This is a very prestigious institute, mainly focused on water health with many international connections. One of the biggest opportunities in this project is offered by the Fraunhofer Innovation Platform, which kicked off in July this year. This platform provides the Rand Water Research Chair and the new postgraduate student with the opportunity to collaborate with the Fraunhofer Institute in Germany. This institute operates at the cutting edge of what is currently possible in water digitization, and it is up to us to create a collaboration where we could maybe import some of this know-how into the South African context to create something really unique. We have a bursary available for a master's and PhD student, and the ideal would be that this person may actually join Stellenbosch University with the prospect of becoming a junior lecturer. For further information, contact Annie Backer at annieb@sun.ac.za.